Okay, so this is week 12, and we will do a summary of what we have learned, right? In this course, okay? Okay, so essentially, in this course, we have been talking about why the results that you used, okay, for probability and statistics courses, right? First year, second year, maybe even some of the early third year courses. Why are those probability results why are they true? Okay, because when you studied at those level, a lot of things were not made very clear. Okay, and there is actually no remedy for that, because in order to make the foundation clear, you need to use some rather abstract mathematics, right? And if you had done it by trying to explain the foundation first, then a lot of people will not be able to use these results, right? Because using the probability results, it's actually not very hard, right? It has a set of rules. It has some sets of rules, conditions, and once you understand those conditions, then their application is actually quite straightforward, right? Just like when you do calculus, right? Derivative, differential calculus, and also integral calculus, right? Once you understand the, if you know the mechanics of it, then basically applying them is not a problem, right? But of course, understanding them at the theoretical level is a different thing, right? So basically, this course is about understanding the theoretical basis of probability theory. Okay, and so for example, things like you are familiar with, like for example, you basically talk about things that you write very casually, right? So maybe A is you, and let's see, A is the event of getting a hit, right? A hit in coin toss. Okay, so even the words like event, right? Now that we know that not every set is an event, okay? Only sets that, so it turns out that only sets in a sigma field, right, can be an event, okay? Because if the set is not in F, we cannot actually assign a probability measure to it, right? But these things you didn't know that, right? At the elementary level, you simply get, operate at a more or less intuitive level. Okay, you say that, okay, fine. You have certain kind of things that will happen. Okay, say getting a hit, and you say that the chance of that happening is 1/2. And when you say something like this, it kind of like a lot of people will say that, well, this is they'll try to understand it as this value as being related to the number of tosses, and this one is the number of hits, right? And they are saying that this value is the final value where this ratio actually converges to, right, as the number of tosses increases. Okay, so a lot of these kind of ad hoc explanations, all right, were given. Okay, actually these were probably the kind of ad hoc explanations that were given to you when when you were taught this kind of probability concepts, right? But of course, you know that this kind of ad hoc explanations cannot unify the entire field of probability, because in some cases, then so coin tosses, you're working with discrete outcomes, right? And then things start to get a little bit complicated, right? This kind of explanations become unworkable when you go to the situation where you work with continuous objects, right? Like okay, so like for example, you have some event, like maybe A is equal to a set of values like this. Okay, so then you want to ask probabilities like this. Okay, and then it becomes very difficult to go to this kind of explanations, right? And the problem with inventing this kind of ad hoc explanations that seem intuitively appealing is that you have to, when you are faced with different situations, you have to invent one explanation, and that is actually going to be very tiring, and you also make people question whether, you know, since you need to invoke an ad hoc explanation at every particular condition, then maybe there is actually no theory at all. You know, maybe what you say is basically just resting on unstable foundations, right? So that's why in this course we already we sort of like work out all these situations, right? And in order to understand these things, you will remember that we studied some background preparation, right? Because in order to discuss these things, you need to know some technical details. Okay, and what did we study from week 1 to week 4? So from week 1 to week 4, so we look at some basic ideas, right? Although we did not involve them direct, we were just studying them as they are, right? But then they turn out to be useful, okay, later. So the first thing was we talked about the set countability, right? The concept of countability of a set, okay? So now we know that if your set is countable, then you have a one-to-one mapping, right? From the set of natural numbers to whatever set you have, okay? So let's say this is A, right? It's a one-to-one mapping, okay? And then you have the idea of supremum and the infimum of sets, right? Okay, and these are the things that they replace. They sort of like they are more general than your max and min, right? Because as we notice, max and min can actually be undefined. If the simplest case is when you have a function like this, right? Say it goes like this. This is 1. Okay. So this function, it sort of like converges to 1, right? Okay. So if you take a sequence of numbers, so you take one value here, one value here, one value here, right? This sequence of values will not have a maximum, right? Because they will never actually reach 1, okay? But you know that their supremum of this sequence of numbers is actually 1, right? Because so the concept of supremum is also related to the idea of bounds, right? Upper bounds. So of course, for this sequence of numbers, you will have it will be lower than 2, it will be lower than 3, right? There are many bounds, right? But your supremum is the least upper bound. Okay. All right. The smallest among the upper bounds. Okay. So this will be your supremum. And of course, similarly, you can talk about an infimum, right? If you start from 0, so in this case, your infimum of xn is 0, right? So this is the largest lower bound, okay? Or greatest among the lower bounds, right? Because it can be bounded from below by -1, -2, and so on, right? But you don't really care about this. You care about the largest among them, okay? So that's the idea of supremum and infimum. And we want to use this supremum and infimum idea because later we consider things like lim sup, right? Okay, limit supremum and limit infimum, okay, of sets, for example, okay, and also sequences, all right? So that's why we need to know these ideas first, okay? And then we studied sequences, right? Sequences of real numbers and sequences of functions, right? So sequences of real numbers are basically just you basically maybe have something like this, right? So sequence is different from a set because the order of your elements is important, right? And then of course sequence of functions, you maybe have something like 1 over x, 1 over 2x, 1 over 3x, right? And so on, right? So the general one is 1 over nx and so on, okay? So here you have some, here, so basically you're dealing with a function here, right? So this is more like you have some function like this, right? This is a case of n equals to 1. Then you have another function going like this. This is a case of n equals to 2. And you're asking if this goes on, right? If this keeps on going, what will happen to the function, right? What function will you get? So this is the idea of the sequence of functions, okay? So when you have sequences of real numbers and functions, then of course you can talk about their supremum, their infimum, and whether they converge or not. Okay, whether these sequences converge or not. All right, so for the convergence, so we have ideas like pointwise convergence and uniform convergence, right? For sequence of functions, right? For basically just if you just have a sequence of real numbers, then there's only this pointwise convergence, okay? And the pointwise convergence, we look at it from a rigorous point of view, right? We use the epsilon method, right? Okay, where we say that your sequence of real numbers converges to L if their absolute difference, right? Okay, of the nth term, right, in the sequence of real numbers from the limit where it's supposed to converge, right, is bounded by epsilon if there exists some threshold, right, some threshold value such that so this is true, yeah. Okay, so you say that your xn converges to L, okay, as n tends to infinity. If there exists some threshold value n, right, such that when your index exceeds this threshold, the difference, okay, the absolute difference between that particular value for the tail, right, the tail of the sequence its difference from the limit will not exceed epsilon. Okay, and we have already looked at that as a, for example, if you have a sequence like the simplest one is this, right? Okay, so 1/2 power of n, all right? So we know that this is 1/2 power of n will converge to 0, right? Okay, so basically this means that so at the lower levels, basically what you do is basically just something like this, and you argue that this denominator becomes very large and this is just 0. Okay, but the rigorous way to argue this is that, so this is 1/2 power of n minus the limit where you think it's going to, and you have to show that for some n greater than the threshold, this will be bounded by epsilon, right? Okay. Yeah. So basically, then in this case, it's simple because this is basically okay, bounded by this, right? Okay, and therefore you bound it with epsilon, and therefore you take log on this part, so you will get well, you can take log base 2, right, to make things easier. So this basically becomes minus n less than log base 2. This, so your n simply needs to be larger than minus log 2 epsilon. Sorry, 1/. Okay. Okay, let me just check this again. You take log okay, so this will be minus n. Okay, so n just needs to be larger than log 2. Okay, so this is an example, right? So this sort of proofs we already look at a lot in the tutorials, right? So I think most of you should be familiar with this sort of arguments already, okay? Because we repeatedly use this argument for other cases such as your uniform convergence, right? A convergence of functions, okay? Okay, so that's some technical details on convergence. And then we have uniform convergence, right? So sequence of functions. Okay, so in this case, we basically have right, this situation, right, where so there is some n, right, greater than this, such that this is true, right? Okay, so this is true for any arbitrary epsilon, right? So, and of course, it cannot depend on x, right? So it has to be. So when you try to do this, you have to bound it with some function that does not depend on x. Okay, it has to hold for all x, right? Then you can say that you have uniform convergence. Okay. So uniform convergence has some interesting properties that you can refer back to the notes. But the most important one is that it allows interchange of limit and integration, right? It allows the interchange of these two operations. Okay, so basically, if you can establish that Fn is uniformly convergent, then the limits of this integral, let's say this is the Lebesgue integral, will be okay the same as okay. So you can move the limit operation, okay, inside the integral, right? Basically, you are exchanging the order of operation, right? And this only works if your Fn is uniformly convergent. There is actually another alternatively, if you can show that you can use the Lebesgue dominated convergence theorem, right? Lebesgue DCT, okay? And in this case, you just need to show that your absolute of Fn is dominated by some function g, okay? That is not dependent on n. Okay, if you have this condition and g is integrable, okay, meaning basically saying that your g is actually finite, right? Then this interchange is also valid, right? So you have actually either one of these will do, right? So either you use uniform convergence, or you can try to find some bound, right? Some dominating function for your absolute of Fn. Okay. Sometimes this is easier to do than this one. Okay. But it basically this result gives you two different paths to justify the interchange of limit and integration. Okay. And then we also look at some set operations, right? Set operations related to lim sup, okay, of some sets and lim inf of some sets, right? And so then just to refresh your definition, right? So by definition, your lim sup of an is if it's supremum, you take intersection first, okay? And only you take union first, then only you intersect. Whereas if you have lim inf, you intersect first, okay? When you intersect first, you'll get something smaller, right? Then only you add them up. So these are the definitions, okay? And we have already shown that so different kinds of this kind of lim sup, lim inf statements, right? Whether this part you have a complement, whether this whole thing you can complement it, they all will involve the use of De Morgan's law, okay? All right, so when you see this kind of we move around identities, right, related to this lim sup and lim inf, basically there's nothing complicated about it, right? It just involves the use of De Morgan's law, right? And you have already looked at some tutorial examples, right, where that is actually given as a practice, okay? Okay, so just be familiar with De Morgan's law, okay? And you should be fine, right? For this part, the lim sup and lim inf. Okay, so basically these are the basic results that we studied, right? Before we actually move into the probability triple, right, where we start to talk about sigma fields and things like that, okay? So then once we have learned all these basic results in week 1 and 4, then we started to talk about the concept of a field, right? Okay, so basically a field you know by now is, what's a field? Anybody wants to give me a quick explanation? Anyone? What do you understand about a field?
The collection of subsets of omega denoted by F containing omega and is closed under formation of complements and finite unions.
Okay, so basically it's just a collection of sets, right? Collection of subsets of omega, right? You have some set that are of interest, right? Collection of subsets of omega with certain properties, right? So basically, what are the properties? So let's say this is your field, right? So of course your omega has to be inside it, right? Okay. And then you have the closure under complementation. So which means if your A is inside this collection, then its complement is also inside it, right? So of course this will imply that the empty set is inside this, because since your omega is inside, so its complement, which is the empty set, is also inside. And number 3, closure under finite union, right? So here we just talk about the finite union because the sigma field is an extension, right? It becomes you basically extend finite union to countable union, right? Finite means you basically just have, so let's say until n only, right? Then their union is also in F naught. Okay, so these things should be actually sort of like very familiar to you. Yeah, it's nothing very complicated, right? It's just you're just talking about, when you talk about a field, you basically are talking about, okay, I have some set of interest. In this case, it's omega, right? In the sample space, and then there are some subsets of it, right? So I form collection, right? Take a collection from it, and then this collection will basically have 3 properties, right? These are the 3 properties. Okay, so this collection has to have omega, and then it has to have closure under complementation and closure under finite union, right? Of course, you know that closure under finite union is equivalent to closure under finite intersection, okay? And I think we already worked that out in class, right? So basically you can work out this result, right? So depending on the situation, sometimes, so since these 2 are equivalent, so if you want to show that a collection of subsets of omega is a field, then you can either show, these 2 are very easy to show, right? They are trivial, okay? So the other one is you either show this or this, okay? You don't have to show both, right? You show one of them is enough because it's equivalent, okay? Right, so this actually forms the basis for our what are the things that can be meaningfully discussed in probability. Yeah. So the field, and actually later on we have the sigma field, right? Okay, sigma field is basically the same thing except that you extend this part to countable. Okay, so basically that means you can work with infinite. You can work with an infinite number of sets here, right? As long as they are countable, right? So basically, when you're countable, you just have A1, A2, and so on until infinity, because your one here can map to the set of natural numbers, right? So it's basically countable. Okay. So instead of having n, you just have infinity. Okay. Now the extension of the field to sigma field is important because without this, right, you will not be able to. If you only stop at the field, right, there are some things that you cannot. Some things that are important in probability, but you cannot discuss it because it won't fall inside the. It won't fall inside the field that you actually are interested in, right? And this happens especially in the situation when your omega is actually an interval. Let's say a unit interval, right? So in this case, can somebody explain why we need to have sigma field? If you don't have sigma, if you don't use a sigma field and extend it from finite union to countable union, then you are going to have trouble when your sigma field is 0, 1. What sort of trouble? Anybody? What sort of trouble? If you just work with, okay, suppose your omega is this, right? And you just work with the field. So you have closure under finite union. Can you assign probabilities to a singleton? Where of course your singleton here is an element in 0, 1. Can you assign a probability to a singleton? Can we talk about such thing? Why not?
Because the singleton is not in sigma, omega.
So, okay, if you construct, okay, you construct a field only, right? So the question is the singleton inside here? Will the singleton be inside your field if you only have finite union? I mean, finite union is equivalent to finite intersection, right? Okay, so in this case, it might be more, it might be easier to talk about intersections. Okay, can you get a singleton from finite intersections? finite intersections of intervals. Yeah. You take some, so this is from 0, 1, right? So you take all sorts of intervals from it, right? Can you create a singleton from finite intersections of these intervals? Is it possible? Yeah, remember, right? In order to be able to talk about the probability of any particular set, right? We need to make sure that the set is inside the this F, okay? So in this case, let's say if you have constructed it using just a finite intersection, will your X be inside it, this singleton? Inside or outside?
Outside.
Why?
Because the singleton is not in the interval given.
Yeah, so the singleton, singleton is basically, you can get a singleton from the following, right? So you have one set like this, then you have another set, right? Half open, that goes like this, right? You take intersection between, this is x minus 2 over n, okay? So, let's see, no, sorry, this is, okay, no, sorry. This is x minus n, so n equals to 1, so this will be n equals to 2. So basically, if you have, you can see that there's one interval here, then you shrink this interval, right? Shrink the left side, right? So you can actually get your x by the following operation, right? Your n, okay? This will give you your x. Okay, you take this interval and then you keep on taking intersection, right? Until infinity, right? So basically, this is a countable operation, right? This is countable intersection. If you just stop at, let's say, k, right? That means finite. Then no matter how big, I mean, if your k, even though it's very large, right, it will still kind of like have a little bit of things left here, right? It won't be exactly x, okay? So if you had used only the field, right, and not the sigma field, then you basically cannot talk about, there's no way you can assign a probability, right, to this sort of sets, okay? All right, so is it clear? The reason is actually because you want to discuss the probability of singletons, okay? It's natural to want to discuss this probability. But if you just restrict to finite union, then you cannot discuss because your singletons cannot be inside the collection of subsets of omega, right? Where you are interested in, okay? That's why the field was actually extended to the sigma field, right? Where you basically just extend this finite to countable, okay? And then your singletons will fall inside your sigma field, right? After you do that, your singleton will be inside the sigma field, okay? Okay, and then therefore you can talk about it, right? You can assign a measure to the singleton. And in this case, we assign the measure of 0, yeah, to singletons. And in fact, we assign a measure of we assign a measure of 0 to countable sets. Okay. So this is finite. This is also definitely countable. All right. So so that's why when you have a line here, right? So when you ask what's the probability of, let's say, getting 1/4 to 1, so the probability of this interval, right? So this interval actually obviously is inside your sigma field. So this basically is just defined as the length, right? The Lebesgue measure of this interval is just 3/4, right? And it'll be interesting to find out, like for example, okay, so this is basically just 0, right? Because the Lebesgue measure for a singleton is actually 0, okay? So in fact, that extends to the situation where you have a countable set, right? Like if you have a countable set, even like something like this, say 1/2, 1/4, 1/8, 1/16, and so on, right? Doesn't matter how big this set is, okay? But it's countable, right? So you have on the real line 0, 1. So you have 1/2, then you halve it, you halve it, you keep halving it, right? Okay. So all these points, okay, definitely there are many points, right? Okay. So even if you want to find this probability, you can assign it now. Then you assign the measure of 0 because simply this set is countable. Okay. So you don't have to invent any sort of ad hoc explanation as to why this is equal to 0. Yeah, because it would seem very mysterious, right? If you do not have this idea about Lebesgue measures, okay, then this would seem very mysterious because this set, right, is definitely is very large, okay, it's infinitely large. So how then intuitively you will feel strange because how could the probability of getting an infinitely large set be 0? Okay, you will feel very puzzled, right? But this will go away, right? Once you know that this is basically just a consequence of having a Lebesgue measure of 0 for singletons. Okay. All right. So this is more like a consequence of operating with your Lebesgue, of you defining the Lebesgue measure of an interval as its length. Okay, so nothing, you don't have to invent any ad hoc explanation, right? Other than the fact that this is just a consequence, okay, of how we define the Lebesgue measure, okay, of an interval. Okay, so with this part settled down, so then we now can formally talk about things like a probability triple, right? Okay, so every time when we talk about any probability statement, it has to be with respect to this probability triple, right? There is a sigma field that we are interested in. Sorry, there's a omega, right? The set of all possible outcomes, right? Okay, depending on what sort of process we are talking about, right? So your omega will be different. If you toss a die, your omega will be 1, 2, 3, 4, 5, 6. You toss a coin one time, it will be HT. Toss it 2 times, there will be 4 outcomes, right? HH, HT, TH, and TT. So it will depend, right? It will depend on what sort of process. And then your F here will basically be the so you need to construct it properly, right? So the simplest one, if your omega is discrete, then you just basically construct the power set, right? Okay. And of course, if your omega is an interval like from 0 to 1, then basically your F consists of your Borel sets, right? It will be so big, right? There are so many possible sets that are inside your F, okay? Because you have countable unions, right? Countable intersections of intervals, okay? And that will also mean that your singletons are inside, okay? But it's a very large set and you will not be able to write it down. All of that. You will basically have a good idea of what it consists of, but trying to write it down is impossible because it's too big, right? And then P is the measure, right? So you assign a measure to the sets, right? So to take note that only elements in F, right? Only elements in F can be assigned, right? Can be assigned a measure, okay, P. So it's meaningful only if A is inside F, right? So this has to be made very clear. Okay. So once you have this, then course, then we have some basic axioms about probability. Like for example, if it's the omega, we will assign the value of the measure of 1. And if it's empty, of course, we will assign it with 0. But actually, this will basically just come from complementation, right? Because, okay, so yeah. Basically, this is basically just, okay. So, right. So since these are disjoint sets, so you can the measure can be the measure of the union can be written as the sum, right, of the individual measures. So if this is 1, then of course, so this is 1 as well, right? So therefore, your P of omega, sorry, P of the empty set is 0. Okay. And then of course you have your other results, right? Your inclusion exclusion criteria, inclusion exclusion formula. Okay, so A1, A2, so it's sorry, this is the union. Plus A2, and then you subtract the intersection. Okay, the same with the case if you have actually 3. So the first part you will add all 3. Okay, add all 3. Then subtract all the pairs, yeah? A1, A2, A1, A3, plus A2, A3, right? It's very easy to remember. So first you do the single terms, then you do the pairs, and then you have the last one, which is all of them together, right? So A1, A2, A3. So the sign here will alternate, yeah? So you have plus, minus, then it will plus, right? So it doesn't matter how many you have. So basically it is just you write down firstly the sum of all the individual terms, then you have the pairs of intersections, and then you have intersecting 3 of them, okay, intersecting 4 of them, and so on and so forth, right? And then you have alternate signs, okay? And then you have Bonferroni inequality. Okay, which basically you have the union, right, of, let's say, okay, the measure that probability measure of union of n sets, right, is bounded by the sum, okay, of the individual probabilities, okay. So this is actually useful in theoretical work. All right, okay. So so once we have the probability triple settled, okay, the issue has been settled already. So now, so then we can actually extend it to probabilities that involve integration, right? And that's when we need to study a bit about a new type of integral called the Lebesgue integral. Okay, right, okay, so let's take a 10-minute break now. All right, and can you check if Spectrum is still on? If not, then you can start to type out your name in the chat box for attendance purpose. Does it work? Okay, so then you just type out your name right in the chat box. Okay, because some of you you didn't update your username in Zoom, so it just appears as some number or something that I cannot identify you with, right? So it'll be difficult to detect, right? So just type out your name, right, in the chat box. Okay, so we are taking a 10-minute break now, yeah? Okay, so let's get started, okay? Right, I'm going to clear this. Okay, so let's refresh a little bit about the Lebesgue integral, right? Okay, so the Lebesgue integral, there are actually many different ways of doing integration, right? So the one that you learn in undergrad first year, that one is the most common one. So the one is called the Riemann integral, okay? But it turns out that there are actually different ways of doing the integration. And Lebesgue integral is one of them, okay? So basically if you have so your Riemann integral, you basically, let's say if you have a function curve like this, so you want to find the area under the curve. So basically you divide into regular, you can divide into regular intervals, right? So then you make a projection, okay, upwards, okay, and basically you just form rectangular bars, right? Say from rectangular bars, okay, and so basically you can, okay, the idea is to use approximation, right? Okay, so you have rectangular bars like this, right? Approximating the sum of the rectangular bars approximates the area under curve, right? The area under the curve, okay? So basically you make the interval very fine, right? Make interval very fine, right? So basically you reduce the interval here, so your bar will be finer, right? So basically you take the limit, right? So you make, so this is the number of bars, okay? So will be equal to the integral, okay? So this is the part that you are familiar with, all right? It's the Riemann integral. The Lebesgue integral works on not on creating partitions. It doesn't create the intervals on your x-axis, but it works with the y-axis. Okay, so it actually makes cuts on the y-axis. Okay, so just to illustrate, it also starts on with an approximation, right? So let's say I have some curve like this. Okay, it doesn't matter, some arbitrary curve, right? So then you have, so let's say you make partitions. You make kind of like this, like this, like this, like this, like this. Okay. So then you make a projection, right? When it touches the function, you make a projection downwards. Okay. Let's project downwards. Okay. Projection, projection. Okay, projection. Okay. Project down, project down, project down. Okay. Right. So this is your y1, y2, y3, y4, y5. Okay. So they will induce sets. Okay. So here you have an interval here. So these intervals are basically, you can think of them as sets. Right. So there are different sets here. Okay. So this is in fact, there's another set here. So there's another set here. So you can call this set A1, you can call this set A2, you can call this set A3, you can call this set A4, and so on, right? Okay. So then, okay, and then you basically, so for this interval, right? Like for example, like okay, let's start with A1. So for this interval A1, then we look for the infimum, yeah. Look for the infimum of f. Okay, so this is my f. I look for the infimum of f for values, right? Here, let's say it's omega. So for values of omega in A1, right? That means in this interval, I look for the infimum of this function, right? And obviously the infimum here is 0, okay? So I will form a, so then basically I will take that and multiply with the measure on A1, right? The set here, okay? Okay, so since this is, so if you have a, let's say this function is actually a regular function, so it means it's continuous everywhere, right? On this interval, and it's also differentiable. So this is a regular function, right? Let's just make it easy here. So you have a regular function like this, so your measure here will basically be, your measure here will be the length, right? So this will be the length, okay? The length from let's say here to here, right? So the length, the measure, okay? So basically, this of course will be 0, right? Because the infimum here is 0, okay? But then for this interval A2, over this interval, the infimum of f is actually here. So you basically, your rectangular bar is here. Okay, when you take the infimum, okay, for A2, yeah, for this interval, you multiply with mu A2. That's basically, mu A2 is the length here, right? And then your infimum f is basically the height here. So basically, it's this rectangular bar. It's also working with rectangular bars, but in a slightly different way than your Riemann, okay? So similarly, then you would have this rectangular bar and this rectangular bar, okay? So over here, your infimum is here, right? Because your function it's like, it dips down. So the infimum is actually in the middle. So your rectangular bar is here. For this one, so it is here. This one is here. This one is here, okay? So over here, the infimum is here, 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 and because here is 0, right? Infimum is 0, okay? So then basically what happens is that your Lebesgue integral is approximated by the sum, right, of infimum F, okay, and mu times the mu of AI, right? Okay, so basically this one is these are the rectangular bars, right? And you're basically just adding them up, right, with the sum. So this is approximate, okay? So if you make this cuts fine, right? So if you make your this cuts, okay, or the horizontal cuts, if you make them very fine, right? Eventually, you will actually get the area under the curve, okay? So that will be so in that case, we would write it like this, like the supremum of this, okay? Mu AI, okay? So basically, this is just your supremum means you cut it in such a way that this sum, right, is as large as possible. Okay, it reaches the supremum, right? When it happens, of course, it will be just the area under this entire curve, right? So you can see that it's actually not very technically, it's not so useful as your Riemann integral, because here it just says sup, right? So it's just kind of like a concept here, okay? Operationally, it is actually very difficult to do this, right? So the soup here is actually a concept, right? So it's just saying that if I make cuts sufficiently many, then I should be able to find the supremum, right? So fortunately, you don't have to really worry about that, because usually if you're going to work with in certain situations, you can actually the soup will not bother you too much if you are working with step functions, right? If you got step functions like this, okay, then basically then it's very easy, right? Because your area under the curve is basically just these rectangles, right? So the soup will not bother you in the case where you are applying Lebesgue integrals on step functions, okay? Because you basically it's just the rectangle is very clear, okay? The soup basically is just a rectangle, right? In other cases, your soup base your Lebesgue integral is actually equal to your Riemann integral, right? So basically, like for example, over here, you say the soup, right, is just area under the curve. Well, if your function is actually regular, then it is just equal to the Riemann integral, right? Okay? You're just trying to find the area under the curve. One is cutting horizontally, one is cutting vertically, right? But they all lead to the same thing, okay? So the Lebesgue integral, in a lot of cases where if your f is regular, it's just your Riemann integral. So you can actually use the mechanism of the Riemann integral to evaluate your Lebesgue integral, okay? But it's just that but the concept here will be very important, let's say in deriving some theoretical results. Whereas the Riemann integral basically is just like a machinery for calculation, right? But the Lebesgue integral is richer in terms of the theory. As you will see later, when we actually try to find things like the expectation of random variables. Okay. Right, so that's your Lebesgue integral. And
Doctor.
yeah.
You said before if the function is regular, and then we can just simply Lebesgue integral is equals to is same as Riemann integral. So what if means like I can do two methods here. So one is the normal Lebesgue, and also one is the Riemann. So which one would you prefer? if this
it's not what I
if this
prefer.
came out in exam.
Okay, it's like this. Okay. Now, if you have, let's say this is a normal distribution. Okay. Square root of 2 pi sigma square E of minus x minus mu. You can ask questions as we talk, right? No problem with that. So, okay. So now your fx, this is a normal density, right? The normal density is regular, right? It's regular over your real line, isn't it? Correct? Yeah, agree, right? Because it's continuous along the real line and it's differentiable everywhere, right? So therefore, if I want to find the Lebesgue integral of, let's say I write something like this, and I say that I'm interested in 0, 1, right? Let's say. How would you evaluate this? This is a Lebesgue integral, right? Definitely, correct? Right, because here, this is the measure, right? So it's like I cut, so here there will be like say 0, 1, let's say, well, let's make it easy. Let's make it easy. Make it easy so that it is the standard normal. Okay. 0. So I want 0, 1, right? Okay. I want area under the curve here. Okay. Now I can say I want the Lebesgue measure. So Lebesgue measure for this. Okay. Which basically is, okay, the Lebesgue is basically saying that this is taking the supremum of, then you make partitions like this, right? Okay, so in this case, since you probably will just get maybe some bars like this, right? Maybe you have one more here, then maybe another there. Okay, so then you make it final, right? So, but then you're still basically trying to find the area under the curve here, right? From 0 to 1. So the Lebesgue machinery here doesn't really give you any. So the most you can do is you can do until like here, right? Okay, mu of A1, right? So it doesn't allow you to evaluate, right? But then since this is regular, you know that you just want the area under the curve here, right? So it is the same as your Riemann, right? So then you will say this is just 0, 1, 1 over square root of 2 pi E of this. And so this one you can just check your statistical tables, right? Okay, for basically this one, the statistical table, they use numerical integration to find it. Okay, so then you get your answer here. So yeah, so in this case, of course, your Lebesgue integral is just the same as your Riemann integral. And of course, your Lebesgue integral doesn't give you a way to, it doesn't give you operationally, it doesn't give you a way to do it, because here you see it just says sup, all right? Unless your function is actually a step function, then sup actually is easy to evaluate, because when you have a step function, like say function here, right? It doesn't, you have a, let's say you have some interval here. So basically this is more or less done already, because this is a flat line, right? So your infimum is basically just this line itself. And there's nothing else, you see. So then in this case, you will want to do your Lebesgue. In fact, it's just a rectangle. You just use the geometry to do it, right? This is the measure and this is the height. This is the measure, this is the height, okay? So yeah, it's not an issue of my preference. It's like, it depends on what function is being discussed. Of course, you will know that in some situations, your Lebesgue measure will actually work, but your Riemann will fail. And that example has been discussed several times already, which is the case where actually you can't sketch this function, right? The function where you have, this is 0, 1, right? Okay, you set it to 1. If your x is You set to 0 if your x is rational. So you set it if it's irrational, right? So for all the irrational numbers, so they're all like here, right? They're all at 0, right? But then for the irrational numbers, they are all like in 1, right? But then this line here is full of holes, right? Okay, it's so actually you can't draw this line because you dig out so many holes because there are infinitely many rational numbers, right, between 0 and 1. So this line cannot actually be, I mean, strictly speaking, it cannot be, it's impossible to draw it, but this one is just like conceptually you know it. So in this case, right, if you want to evaluate the Lebesgue integral of f d mu, you can, you know, if you use the Lebesgue integral machinery, because then you will basically just separate it out to the two parts, right? So this part is the x rational. This part is x irrational, right? Because the union of rational and irrational between 0 and 1, you get the length, okay? And this is equal to, so this one is equal to 1 because here it is 1, right? Okay, right? So here you know that this set is countable. Which part is countable? This part, the part that's rational is countable, right? So you know this is 0, and therefore this becomes 1. Okay. So in this case, only the Lebesgue integral can give you a value, right? But this is easy to do because it's just a step function, right? In fact, it's just a constant here with a lot of holes. But the holes don't matter to you because, you know, at the places where you have holes, right, the measure is 0, right? The measure of your this set here, right, is actually 0, right? Because it's a countable set. Okay, so it doesn't affect you, right? The measure for the set of the irrational number is still 1, right? Okay, it's 1, right? The measure of the irrational number is 1. And then the height here is 1. So therefore you get 1, okay? For this part. If you try to use here, your Riemann integral is not going to work. Because there's no way for you to find any kind of meaningful partitions on the x-axis here. Okay. So only in this case, this of course is a theoretical kind of situation, right? But it basically extends probability. Okay, now because so most of for practical purpose, right? For most of the models that we use, we usually use models that the probability density function is regular. Okay, because that gives us a lot of advantages in terms of the theoretical properties are good. But when you introduce Lebesgue integral inside into the picture, it means that you can basically discuss probability models where you know, you don't have to have your f being regular. Okay, your f doesn't have to be regular, and yet still it can function as a probability density function. Okay, that means you can still do probability work on those kind of models where it is not regular. Right? So this, of course, it greatly extends the range of models where probability theory can deal with. Okay, of course, when you study you study the models, right? Those what gamma, exponential, normal, whatever. Those are all regular models. Okay, because regular models, they are well behaved and they are easy to discuss. Okay, but probability theory is bigger than that, right? So you can basically extend it to cover even non-regular probability density functions, right? And only the only when you use the Lebesgue integral framework, you can discuss this. If you just confine to Riemann, you cannot. You will just get stuck with regular models. Okay, so that's the idea of talking about Lebesgue integration. Okay, is that okay for you?
Yes, thank you, Doctor.
Okay, sure. Okay, let me clear something here. Okay, clear the screen. Now, of course, when there are some results related to the Lebesgue integral, whereby, like for example, if you integrate over some set here A, so this will be the positive part minus the negative part, right? So the positive part will be like, for example, your function can be like this. Okay, this is your f. So you have a positive part, which is this part. Okay, the part that's negative, you set it to 0, and then okay. So this is your positive part. The part that you have the negative part is this part, right? So you only consider, so the part that's positive, you put 0. The part that's negative, you flip it up. Okay, like this. Okay. So then basically because you don't want to deal with negative, like most of us, right? We don't want to deal with negative people, so we don't want to deal with f that's negative, right? So we try to work with positive f. So here that so it makes it easy, right? When you want to discuss Lebesgue integrals for positive functions, it's very easy to discuss, right? You just make cuts like this, then you can find the rectangles. Okay, like this. Okay, so then basically you take subtraction, right? So then this will be equal to the Lebesgue integral of the whole thing. Okay. Okay, so that's the just some small parts about the Lebesgue integral, right? Some operations. Okay, but of course, if this is regular, if your f is regular, okay, over this interval, like for example your trigonometric functions, then of course this will basically just be over your a's or f x dx, right? Your Riemann. Okay, if your f is regular. Okay. Okay, so and then we talked about the random variables. Right? The idea of random variables. So previously we were used to writing things like this. Right? For example, you write it as this is what you would write when you are talking about a binomial model, right? So then this is like, then you say this your x is the random variable for, let's say, maybe the number of heads in n tosses of coin, right? So of course this worked very well, I mean, for at lower levels, right? But then now we know more about, now that we know about the probability triple, so we kind of like know that, okay, so this is a probability measure, and this object here has to be something that is inside F now, right? Because previously you don't know that, right? We kind of like just say, oh, okay, X is a random variable, so it feels a bit fuzzy, like what is a random variable? A lot of people just think that, oh, it's a variable that's random, but it doesn't really explain anything, right? So, but then it's kind of like people usually just say, oh, okay, so it's some quantity where different values can be assigned probability value. Okay, people accept it like that. Like for example, I can assign for 0. For the 0 outcome, I will assign the probability of in this case will be 1 minus p power n. For 0, I will assign this probability. For 1, I will assign probability np 1 minus n minus 1, and so on, right? People just understand it like that. But since we studied this already, so we can now finally understand it fully, right? Where we understand x as a set function. Okay, from x, so sorry, from omega to some image of omega. Okay, and in fact, I think we have emphasized this several times already, right? So this thing here has to be some object in F. Okay, so what is happening here? So when you say Px equals to x, for example, what you are really saying is that you are saying something like this. Okay. So this statement basically is talking about a set in F, and the way we look at it is we construct our F here, and then so of course so your F here is easier to discuss this if you are working with discrete cases, right? So you have omega. So then you map to some space here, right? So in this case, let's say this binomial, so you have 0, 1, 2, 3 until n, right? So you will map certain values will get mapped to 0. Some values will get mapped to 1. Some will get mapped to 2, right? For example, so here you have, and some will get mapped to n. Okay, and then of course this will be the elements where you have let's say this will be to make it easy. Let's say binomial case. So let's say your n equals to 2, right? So let's say you'll have a coin toss HT and TH and TT, right? Okay. So then basically you only have, so you can say that you can map different things, right? For example, HH you can map to 0, all right? You can map HH to 0. You can map HT to 1. You can map TH to also 1. And you can map TT to 2, right? Okay. So then you have these are the collections with one element. Then you have collections with 2 elements, collections with 3 elements, and collections with 4 elements, which will be here. Right? And then of course you have collections with 0 element, which is your empty set. Right? So of course you can list them down, right? So now we understand that when we say x equals to something, right? Big X equals to small x. Basically, we're saying that, okay, we come from, let's say, HH to 0, and then we map it to here. So this is the inverse. So you take this and put it here, right? And the reason is because you can only discuss things that are inside your F, right? So you have to have, when you say your X is equal to X, it basically means that you are first doing a mapping. You take the set in omega, go to this mirror, so this image space, and then you have an inverse mapping that puts it to the F, okay, the sigma field. So 1, it will put into I think 1, it should put it to, you will put to HT and TH, right? There's 1 head, so you put to this set. Okay, 2, we will put it to TT. Okay. So now it is in this sense that you basically can talk about Px equals to 0. Yeah. So when you talk about Px equals to 0, basically you are talking about this set. You're talking about x inverse of 0 is equal to okay, HH. Okay, and this one you can assign a measure to it, right? So since if you assume that the coin is fair, then all outcomes are equally likely. So you can assign a measure of 1/4 to it because there are 4 outcomes. So this is one of them. So you can assign 1/4 to it. Okay, right? It is in this sense, yeah. One of the students asked me like, why is it the solution? One of them is like I kind of like write like this, but then the other one is like what I'm writing it like now here. There are some of the lines are crossing each other. Actually, it's the relationship that's important, right? Not whether the lines cross each other. Okay. I write like, I mean, like this is definitely tidier, right? If I draw the line longer, I put it at the back, then these lines will not cross like this. So it basically just to make the presentation tidier, all right? Because sometimes when I write in the lecture, I kind of like just write it without thinking too much about being tidy, okay? So that's why you see like in this case, I have like the lines intersecting. Of course, with some careful thinking, you can basically arrange this thing, right? In fact, you want it to arrange nicely, I will arrange it like this. So here is my omega, here are the elements with 3, 2, 1, and this is 0. So then, yeah, then I'll draw the things like map here and then map to 1, then whatever gets mapped to 2 and so on, okay? It will be much tidier, all right? But then again, it's the relationship that actually matters, right? So as long as you make the relationship clear, it's fine, okay? And then, okay, so I think we're just running a bit out of time already, so it's okay. We will just stop until here. So on Thursday I will continue with the summary, right, on expectation of random variables, right? But this part I hope is clear to you because this is very useful. If you are able to draw out the diagram like this, you more or less understand what a random variable is already, right? By relating it to the sigma field, okay? Right. I think the so I think this part here, understanding what a random variable is important. Yeah. Okay. So so these examples will help you. Okay. Okay. So that's all for the summary up to this point. So you can also think about, as you study a bit, you can think about if you come across questions and you want some clarity, okay? You can just ask on Thursday, all right? Okay, so, all right, so I'm going to stop the recording now.